right? We typically identify our data in a data model. We think about our data as defined by thematic layers. There's a layer for elevation. There's a layer for land use. There's a layer for air pollution concentration. There's a layer for soil type. There's a layer for population density. So we have these various layers with different features represented, different themes represented in each of the layers. It's an easier way to mix and match, to pass around different data layers, and we can then create synthetic layers by combining layers. You're interested in places that have a high probability for erosion. We might have both steep slopes and soils that are likely to erode. We can combine those and come up with an erosion layer, erosion propensity layer. But by separating them by themes, we have the greatest flexibility and the greatest ability to update one set of variables without having to mess with others. Our data model typically has the real world and then this abstraction. So we identify features, right, that are from entities. So we have something out in the real world, and we're going to create a polygon feature, a lake or a wetland. And then we're going to record a subset of properties for those. And we typically think in this data model. We look at maps that have these polygon features identified and look at the attributes that we use to define those polygon features, the measurements. And so we're kind of abstracting the real world to this data model, which is a subset of what's out there. The wetland might have lots of properties we're not going to record, a lot of detail in the shape that we're not going to record because we just have a certain level of detail. Underlying all that is the computer representation, the bits and bytes, the ones and zeros, the data structures that we sometimes have to think about, but usually not on a day-to-day basis. Often we think about these most when we're entering them, or we get into some strange resulting analysis that might come from how we represented our data. But for the most part, we're thinking in this data model. There are two main data models we use here. There's a vector data model where we use points basically either alone, connected in a line, or combined around an envelope to enclose an area to identify features. The other is a grid. The grid is pretty light here. We have a grid with cells. It's a checkerboard. And that's a raster data model. So the vector data model, we use just points alone or combined in various ways to identify individual or singular features, linear features or area features, or a raster where we fill values in cells singly for points, in a connected linear way for lines, or in a group of cells together for area. So this is the checkerboard. This is sort of free-for-all. The idea really, the main difference between a raster and a vector is this is fixed in its organization of where we're going to measure things. And every place has a value. Even the nothingness between the line and these points have a value. In vectors, we're only paying attention to where we have data. In between is a great nothingness. There's nothing defined there. So we can only talk about our features, or here we can talk about space between features. This is much more compact. It's a much more natural way for many kinds of features, discrete features. So if we have, for example, buildings or cities and city boundaries or countries, those are, you're either in or you're out of the country. You're either in or out of the city boundary. You're either on or off somebody's plot of land. So it's natural that we identify things using these vector data layers. They're discrete objects. Rasters are better at describing gradients. We can do the in or out, right? We have a code for one parcel and not for another, a different code, so you can say whether you're in or out of the area. But we can also represent continuous features by at each of these points having a value. So rasters tend to be for continuous features or for data that are collected as rasters, where vector are more often for discontinuous features or discrete features. Now I talk about these coordinate systems here. I have this X and Y coordinate. I haven't really introduced it. I'll do that now because we're really used to working in a two-dimensional Cartesian coordinate system where we have right angle axes and a uniform linear scale in both directions. And that's what we use for most of our analysis. Remember I said we had layers here? We're abstracting the world into these flat layers, but the world isn't flat, and we don't really have these layers everywhere. So this is a Cartesian or a flat system. The world is curved, and we're mapping things on the surface of the Earth. So we're using a spherical system, a latitude-longitude system, where it's 90 degrees from the equator to the pole in both directions. So it's 180 degrees on any one side. That means 360 degrees to go all the way around from the equator through both poles back to the equator, or it's 360 degrees around if we go in the direction of the equator. So we have this, from the Babylonians, a spherical system to identify this 360 degree rotation in either directions. And we have two cardinal directions, north, south, and east, west. So if we go from a starting point on the equator at 0 latitude, 0 longitude, the number of degrees in one direction in longitude and another degrees in another direction latitude, so longitude here in the east, west, and latitude in the north, south, we'll get to a location. If we know the radius of the sphere of the Earth, then we know where we are on the surface of the Earth. We split the degrees into 60 minutes, so each degree is 60 minutes, and each minute is 60 seconds. So the degrees, minutes, seconds for our latitude and longitude system. Now again, this was adopted by convention a long time ago for a bunch of reasons, and we still use this rather than a base 10 decimal system because of convention. Now, we have to get off of that and onto a two-dimensional system, and we use a three-dimensional Cartesian system going from the center of the Earth out through the equator in 2 dimensions and then through the pole in another dimension. So the X and Y are in the equator. We have the globe fitting in here. We use this because it's easier for a bunch of calculations, and then we can go from that to this two-dimensional system, or we can go from the lat longitude to this two-dimensional system. Geodesy and projections, what we'll talk about next week. For now, just think about this two-dimensional system and trust that we have a way of getting there from our spherical system. Right, so the spherical system's on the surface of the Earth. Next week, we'll talk about how the spherical system actually isn't a good approximation, and we have to flatten the Earth from the poles, and it even gets more complicated. But for now, just think about this two-dimensional system. Right, we have 3 kinds of things we typically follow, really 4, but we have points, lines, and areas. And then sometimes you can densify those points all across the landscape for a gradient or continuously variable surfaces. So we do have 3, and we apply points in a special way to get a 4th. Points are any feature, we just are interested in one central location for that. They aren't points in real life in that they don't have any dimensions. In mathematics, a point has no dimension in any direction, it just has a location. Well, if we're going to use a street light, or a fire hydrant, or even a lake, or a house, and have a point feature represent that, clearly the point is an abstraction because the point doesn't have anything but a location, but these things do. What we're saying when we represent something as a point is, I don't care what its physical dimension is. That date isn't important to me. I'm not going to represent that. I'm just going to represent its location because that's important. Lines are linear features, a set of connected points. And again, we're saying we don't care about the width of it. All we care about is where that line runs. In areas, we're saying, well, now the size, the shape, the dimension has import. So we have a set of connected points or lines around the perimeter that define this area. Points, lines, and areas. Now, we typically have our layers where we have lines defined by points, and these lines may be grouped together to define areas, and an attribute table associated with it. In this case, this is a polygon data layer, and here I have various lines. Here's line 102, 101, 105, 103, and I have associated with each of these polygons an identifier, and I'll have an attribute table. And that attribute table will have typically an identifier and then other variables of interest, its type and its area in this case. So attribute for this basically first polygon here is in a table with an ID of 1 that connects it to that first polygon, or 2 or 3. So there's a connection between entering the attribute table and the features that I'm representing. Underneath that, there's a bunch of embedded information, topology and coordinate data you don't see explicitly. Sometimes you can query that and pull that out, but there's a bunch of organization going on. So it, for example, will know that polygon 1 is created from lines 101, 102, and it creates information on their connection and order and where they intersect. And it will then relate these lines to their nodes and vertices, right? So there's a node 58 and 47 and 48 that identify line 101 that create line 101. And then there may be other information connected to the vertices, which it's in X and Y and the type of it and a number associated with it. So there's all this information that records structure and topology that are inside the system that you don't see. Remember, I said earlier on, we take a data model view, so we're looking at this. And this is sort of that computer stuff, the data structure that's hidden underneath. You have to know that it's there. You don't have to need to know too much about it. But when you create topology, you know, oh, I'm creating a structure. When you digitize, oh, I'm creating a structure in a certain way. Now, again, we typically have a data layer with objects identified by an ID and then a set of attributes associated with them. So building name, floors, roof type. Nobody's one definition is better than another's inherently. You add the attributes you need depending upon your use for the data. So you can add or delete them. Now, if you add them, you have to go, if I want, in addition to roof type and floors, the wall type, the exterior type, I would have to then add a variable for that and go to each of these buildings and fill that attribute. So I have each of the rows here with each of the attributes. If I add a new attribute, I have to go collect it. So everything has a cost. In a raster data set, we have a fixed cell size. We typically have the axes of the rasters, so the edges, aligned with our coordinate system. And we have cells that have a cell dimension the same in both directions. A 1 meter raster, 2 meter raster means it has a cell dimension of 1 meter or 2 meters. And I have the coordinates of the lower left cell or coordinates of at least one of the cells. And then I can, if I know the cell dimension, calculate where I am anywhere in the raster. Rasters are great for gradients. So here's an elevation raster, and you can see from the highs in the greens to the lows in the reds, ascent. So I'm going downhill here. There's a ravine here. There are these cells that define the raster on top. So if I zoom in, I can see each of the cells. And then I can do things like look at the actual values. So each of the rasters has a cell at the center of the cell. Now, whether you interpret that as being over the whole area or at the center is more sort of epistemological. It's how you think about the world. But in this case, we really assign it to the entire area. If I land anywhere in this, for the most part, the default is to pull the value that I find at that cell center. If we interpolate to a finer or coarser raster cell size, I interpolate to the new cell center and assign the value there. It's not really important in most applications which of those epistemologies you establish. Just know that it's the cell center, and some people can interpret it as the entire cell, right? So we have kinds of data. That means the kinds of values that can be put in a raster or in each of our attribute columns. And there are three main kinds. And you have to be careful to identify these because the math on them can be different. You can inadvertently have errors if you mix them up and you're not aware of it. So nominal ratio is type, right? It's kind. It's a duck, it's a dog, it's a cow, it's a house. Right? There's no way to say a cow equals 4 houses directly. They're not on the same level, right? There's no implied rank or size. They're different. You got to be careful because people often give numbers to nominal types. So it'll be a class 1 or class 2 or class 3 or class 4. You can't do math on those classes and have it make sense. Just like you can't do math on houses. You know, 1 house divided by 2 cows equals what? Nothing. All right. So nominal data is just type. Got to be careful because the JS will often let you do calculations on nominal types. Right. Ordinal data identifies order. It's a little more, quantitative than nominal. The ordinal data says, well, if I have a 1, it's bigger than a 2, and a 2 is bigger than a 3. But I don't know that, a 1 to 2 is the same distance as from 2 to 3. 1 may only be 10% better than 2, but a 2 may be 300% better or bigger than 3. It just ranks them. This is above or below this other number. So ordinal data basically allow you to rank things, but they don't tell you where the relative value is on those rankings. An interval ratio are numbers as we think of them in algebra on a scale. The same scale, they're linear, something like temperature, population density. 40 degrees is twice as warm as 20 degrees. It's on a scale that means something. And again, the only reason, or the main reason I bring these up is you have to be careful because you can do some interesting calculations. For the most part, if you're doing quantitative calculations, you want to do them on interval ratio data. The ranking or nominal data we can use selections on. And so we'll be having to keep this in mind. Lots of beginners and actually lots of fewer, but enough established users don't check to make sure they're not calculating on ordinal or nominal data. Right? So here's a set of data. Is it nominal, ordinal, or interval ratio, right? They're categories. You can't divide mixed forest by evergreen, and you can't say evergreen is bigger than or better or somehow than deciduous uniformly. So these have to be nominal data. Okay? Same thing here. This is a human appropriation of net primary productivity, grams of carbon per unit area per year, right? Where the farms are, where the high population density is. So you get this productivity, and in the natural landscape, it all goes to nature. In human-dominated landscapes, it goes to humans. Right? There's a lot of agriculture. And so in this case, this means something. It's grams of carbon per year. It's a direct measure. This is interval ratio. I hope you're getting the drift. Population count in persons. Is this nominal, ordinal, or interval ratio? Well, this is also interval ratio. I mean, you might think it's a count, so it's a whole number. It's an integer. You can't have half of it, but population of 10,000 is twice as big as a population of 5,000. So this is clearly interval ratio. Right? Crop type, nominal, ordinal. You probably know that, right? Population density by county. Again, or interval ratio in this case, or nominal in a lot of the cases. Travel or health risk. Well, this is ordinal. Right? It's ordinal because it's low, medium, or high. Very high, rapidly developing, but you know that one's lower risk than another, but you don't know by how much. Is it twice as risky to go to, I don't know, the Ukraine versus Poland, or is it 7 times as risky? You just don't know, right? You just know it's higher. Okay, so I think we've gone through that enough. One of the things you have to know, it's a different topic now, is that there's enforced uniformity in vector polygons and in raster cells. And that's never true, almost never true. Right? Never say never, except when you say never. The polygon here, it's a bed plantings in front of Coffee Hall, has an inclusion of the sidewalk because they didn't have the time or money to include these small areas. You always have a minimum mapping unit below which you're not going to map things. You can't spend all day mapping every dirt clod, every leaf of grass. So you have an area below which you say, I'm going to accept inclusions. And those are true for any vector polygon, along any vector line, or in any raster cell. You can never escape this. You have to basically make it such that things of that size aren't going to change your analysis. They don't matter to you. Right? So you have a minimum mapping unit, and below that, inclusions don't matter. Right? Almost nothing is pure. So almost everything has at least a little mixed up in it. And you have to, every time you have a data set, say, is that key to me? If I have one bit of water in this land cover map, even if it's a tiny inclusion, is that important for my analysis or not? If I'm looking at distance to water to try and establish new water holes, and they have permanent water out of location, then yeah, it does. My data set isn't useful for me. I have to either go to a smaller minimum mapping unit or one that identifies those water locations. But if it's something like, well, okay, inclusions of chalk a small or rocks in a field and it's just a small portion of rocky soil, well, I don't care. And you see that in data. So this is the Natural Resource Conservation Service Soil Survey Mapping description, and it says areas of soils that were remarkably different in use and management, but too small to be delineated, the scales of mapping were described as inclusions. And they, in their literature, tell you how big the scale of mapping is and how big these inclusions will be, but they're saying these may be there up to a certain size. And you can get the idea when they're creating the soils map, they're walking across the landscape and identifying areas that are of a uniform soil type. Well, you can see variation here in the color that associated with the chemical and physical properties of the soil that vary. So this is plowed soil, and here we have a road going along the edge of a drainage ditch in the soil. And so when we lay a raster on top of that, the soil is not going to be uniform. I'm going to get characteristics from inside a mixed area. And you have to know, well, what's the level of that mixture? Same sort of thing here in this mixed pixel problem, right? Does land cover water or land? Because this is the landscape underneath it, but I have to assign a value to the raster. And this is pretty easily land. Yeah, that's fine. And this is probably going to be water for most people, but you have to decide how is the assignment going to be made. If there's any water in it, will you call it water? Is it the majority of the surface? So if it's mostly land, it's going to be land. Or if there's any land in it, will you call it land? And those different rules will affect how your output looks. So it has to be written in the metadata about your data, the information about your data. You have to know how things were assigned and what the characteristics of the inclusions are, and know the quality. Another thing you have to know is there's a difference between how rasters and vectors tend to store attribute data associated with the geographic data. So I have a one-to-one relationships typically between features in my vector data set and rows in my vector table. Right? So here's an ID for this vector data set. There's an A and a B and a C and a D and an E. So I have an entry for each of these. I have a class then and an area for each of those. And so there's a one-to-one relationship between features and entries in the rows. We typically don't do that with raster. So here's a raster equivalent, right? I have my 4 areas, and then my 5th one down here in the corner, where I have basically a bunch of cells, and I only have a row for each of the categories of cells, right? There were 5 in the previous one, A, B, C, and D, because this little corner was separate from here. In most raster representations, I don't do that, right? I have an entry for each of the different kinds of attribute that I'm going to represent as the main attribute, each of the IDs in this case. So I have 4 here, but I don't separate the features in the table. Well, why would I do that with a raster? Right? Why don't I have different ones? And the reason is that I have too many cells. If I have a continuous variable, I might have a different value in each of these cells, and then the attribute table would be an entry, a row for every cell, and I can regularly have tens of millions of cells in large raster data sets. So I'd have tens of millions of attribute entries in the table, right? Tens of millions of rows, and that just is not workable. It's not feasible. The table gets too unwieldy to handle. I can kind of fake it. If each individual blob, it has the same value as another blob, another set of contiguous raster cells, there are ways to go in and recode them so you have each unique area has a unique code. But for the most part, we only do that in special circumstances. For most of our analysis, if we're interested in individual features, we use them in a vector data set. And if we need to then combine them with raster, we can convert them right before we do the combination, convert the vector to a raster. And so you have to be careful. Remember, these attribute tables are different. So in raster to vector conversion is that sort of compression of the attribute table, if I go from a vector to a raster, going to affect my analysis later on down the line.